Hello there and welcome to another video looking at flat earth. What else? This video is kind of carrying on from a video I did last summer actually, in which I looked at an example of a person standing next to the seashore, so their eyes were 6 feet above the sea, and considered what they would see as they looked out to the horizon, and showed that the sea would look flat and the horizon would look at eye level and the horizon would look flat. Well, flat earthers complained that it was only at 6 feet, and they also complained that I used very complicated mathematics to confuse them. I used mathematics that's taught to 14-year-olds, so that was completely outrageous of me. I should have realised that. But anyway, in this video I'm going to look at a similar type of example, except the observer this time is going to be 1,000 feet above a sphere with a radius of 3,960 miles. And I'm not going to do the calculations, I'm going to actually visually demonstrate how much curvature there should be. So you can't accuse me of using mythamagics in this one, flat brainers. Right, so this diagram shows you what we're going to be looking at, which is an observer. We're looking down onto the observer here, and because they're on a sphere, there's a horizon around them which forms a circle. If you're 1,000 feet above a sphere with the radius of the Earth, then the horizon will be about 38.8 miles away. So this circle's got a radius of 38.8 miles. We're going to ignore atmosphere or refraction or anything like that. We'll just keep it simple. This is just the geometry. So we're going to consider the idea that a person is here 1,000 feet above. They're looking to the right and they're taking a photograph with a viewing an angle of view of 90 degrees, which you can see here. So this is 90 degrees. And we want to consider, would they see curvature or wouldn't they? Now this circle here, because it's part of a sphere, it's going to have a certain degree of curvature. So what I want you to imagine is if you cut this circle out from the surface of the sphere and then put it onto a completely flat surface, then the edge of the circle would touch the surface, but the circle itself in the middle would rise a little bit above the surface because it's curved. So this line here from left to right, the left hand side to the right hand side of the circle, you could consider this line as being an arc that follows the curvature of the circle, or you could think of it as a straight line that goes straight across following the flat surface. And same with this line here. Now, there are three ways I think you could see curvature if you were above a sphere like this. You might see it between yourself and the horizon, so along this line. You might see it across your view from left to right, or you might see the actual curvature of the horizon itself, this line here. Now, even if this was a perfectly flat circle, this line here would still be curved, so you might still see curvature even on a perfectly flat circle. So we've got to consider, would we see these any of these curvatures? And like I said, we'll consider it from the perspective of someone taking a photograph with an angle of view horizontally of 90 degrees. So they're seeing 90 degrees across from left to right. So the first thing I want to consider is how much curvature does this whole circle have itself? So what we're going to do is we're going to look at the situation from the side. So this is looking down. Now we're going to look at the situation from the side. So here's the observer, and you can see that I fixed it so that they are 0.189 units from this line here. Now 0.189 is miles, so sorry, 0.18 miles is roughly 1,000 feet. So this is about 1,000 feet. So this is supposed to represent an observer 1,000 feet above this line here. Now this line here, believe it or not, is actually part of a circle. And I'm going to convince you of that. So if I zoom out, you can see it's a circle. Now because I've chosen the circle to have such a large size, you can't zoom out on this software to see the whole thing at once. So I'll just show you right around so you can see that it is actually a circle. Now this circle represents the Earth, or a side view of the Earth. Now the Earth is a sphere, so a cross section is going to be a circle, and a line going across here like this will be an arc. Now an arc is just the curved part of a circle. Let's see if I can find it again. Good, I found it again. So yeah, this is a circle, and I'll highlight it so you can see that I've chosen it to have a radius of 3,960 units. So we're using 1 unit equals 1 mile. That's the scale we're using. And like I said, the observer is 0.189 miles, which is about 1,000 feet. So I can get rid of that line just now. So I want to consider a few things on this diagram. Now, first of all, I've drawn the left-hand side of the horizon and the right-hand side of the horizon. So if I get this back up again, this point left and right, and this point right, correspond to left and right here. And you can see the observer is a little bit above. And we can also put in a line, no, not that one, I'll find the right one, that's it. The straight line that goes from left to right. So that corresponds to, remember I said this line here, you can think of it as either the line curving the arc that follows, the curved arc that follows the circle, or just the straight line that goes straight along this flat surface, if you imagine this circle on a flat surface. So, now I'll turn the observer off just now. What I want to do is actually visually show you just how much curvature that circle has. Okay, because this is actually just a giant circle drawn on this piece of software. So there you go. That's the actual circle. That's the side view of it. A circle with a diameter of about 77.6 miles on the face of the Earth. Oops. I can turn the circle off. So that's the perfectly straight line, and that's the curved line. That's what this circle looks like from the side. If you took, this line from left to right that follows the arc of the circle, that's how curved that would look from the side. Not very curved at all. So the whole circle that the person 1,000 feet above the Earth sees is basically a circle with a diameter of about 77.6 miles, which is practically a flat circle. It has a very, very slight curvature, which you can see here because this is a perfectly straight line. Okay. So, let's consider a couple of things. Now remember I said there's different ways we could see curvature, so let's think about what we're going to look at next. So we've considered the curvature of the entire circle, which isn't very much. So let's consider this line here from left to right, which has got a length of about 55 miles. So this line here going all the way across the view, if the person is taking a photograph of the horizon with a field of view, an angle of view of 90 degrees, which is about as big as you're going to get without getting some distortion. Well, I've prepared a little diagram for you to see. So again, this is the same thing. I've drawn a circle with a radius of 3,960, and I've drawn a line on here with a length of 55. So let's close this up so we're just seeing that. So this left and right here correspond to left and right here, these two green circles here. So the person's here and they're looking towards this red circle marked right here. So they're seeing this line from this angle here. So that's their left and right there. So that's how curved it looks. That's how curved a line 55 miles long looks. That's the perfectly straight line, and that's the curved line. So if you were 1,000 feet above the Earth, or a perfect sphere, and you took a photograph of the horizon with an angle of view horizontally of 90 degrees, that's how curved it would look. Well, that's how curved the circle would look from left to right. This is this massive curvature that flat earthers tell us that we should be seeing. This is a line 55 miles long on the face of the earth. This is how curved it would look if you saw it from the side like this. And you can see it is curved because that's a perfectly straight line. Okay, and I'll zoom out again so you can see I'm not cheating. This is a part of a circle, and that's how curved it looks when you see it close up. This is called locally straight. When you look at a curved line up close, it's almost completely straight. That's called locally straight. Okay, so there's no curvature this way. Let's think about this line here, because this line is significantly curved, but you're only seeing it at a very, very slight angle. So these two lines here, imagine these two lines here are drawn on the flat surface. And this line here is on the flat surface. So we want to know what is the angle in your field of view between this line and this line. So this line, these lines will appear vertically one above the other one in your field. Well, they'll look horizontal to the person looking across this way, and this one will be above this one here. So there'll be a certain distance apart in your visual field, and we want to work out what that'll be. Well, we work out how far apart things appear in our visual field as an angle. And we can do that here. So we don't need the circle for this. All we need is the bottom line. And I'll mark a point 27 miles along. Okay, so I've already worked all this all out. So here's the observer. This is the hypothetical flat surface. And what you're looking at are the point 27 miles away, and this is the horizon. This is the horizon on the right. So I'll just remind you. So the 27-mile line represents this line here, but you're looking at it from the side. So you're looking at a straight line along here, a point marked 27 miles from the observer, and a point marked at the horizon. So that's what you're looking at here. So hopefully that's clear. So we can work out what the angle is between these 2 points and the observer. So we work out what's called the angle subtended at the eye for the observer between these 2 points. And it's 0.232. So in the person's field of view, these two lines they will appear horizontally, but they will be at an angle of 0.232 apart from each other. Well, to give you some sense of how much that is, a full moon has an angular diameter of about 0.5 degrees. That's how big it appears in your visual field. So less than half of that. Now, a full moon, you imagine it looks bigger than it does. It's actually really small. So the distance between them is not very big. Now, considering also that if this is a photograph with a 90-degree angle of view horizontally from left to right, then the distance in the visual field in this image is 90 degrees across the way, and the vertical distance between these two lines will be 0.2 degrees. So even with a 90-degree angle of view, you're not going to see this curve because you're looking at it at too shallow an angle. These two lines look like they're right next to each other because you're looking at them from such a shallow angle. These two lines will be almost right next to each other in your field of view if you're here. So therefore, I don't think you would see it. Get rid of that. So you're not going to see this line here. You're not going to see the curve going from across the way. So, and the line from the observer to the horizon is virtually straight, which we can see if I put it back in. So that's the line from the observer to the horizon. Okay. Now what I want to do is also get the angle of depression of the horizon. So I can get rid of that point there as well. Let me get the right line. So that's the straight line. Now this line here is parallel to the straight line that goes through the horizon. And so remember, this is actually the curve of the Earth, this line. So this is the what flat earthers call the eye level for the observer. This is the horizontal line going straight from the observer. So we want to know as an angle how far below this line is the horizon here, which is 38.8 miles from the observer. So again, we can do it as an angle. And it's 0.56. So a full moon has an angular diameter of about 0.5. So how far below the horizon is, how far the horizon is below the horizontal is about the width of a full moon. So it's going to look very, very close to eye level. And I'll get rid of this angle just now. There's a couple other things I want to look at. One thing I want to look at is quite interesting. I'll get rid of that line. We'll put the circle in again. So this is the actual Earth curving away from the observer. And I don't need that line just now. Now what we can do is we can work out as an angle how much of a section of this part of the Earth between the observer and the horizon takes up in their field of view. Okay. So you can see I'm working out as an angle, the angle between this point in the observer and the horizon. Now if we go right to about halfway along, notice that it's at about 0.1 degree, 0.15 degrees. So when the observer's here and is looking towards the horizon, half of the Earth between themselves and the horizon is in a band of view in their visual field of 0.15 degrees, virtually invisible. If we go along a bit further, it is quite astonishing how little they actually see because they're looking at it at such a shallow angle. So there's 0.5 roughly. So this is about 3/4 of the distance between themselves and the horizon. So that's about 30 miles roughly. Is going to be in their visual field within a band that's about the same diameter, the same width as the diameter of a full moon. So even this whole section here of the Earth between the observer and the horizon is barely visible to them. The only part of the Earth that they see when they're looking up towards the horizon that they really see clearly is very close to them. They're only going to really see this bit clearly. Once you get to this bit here, it's virtually invisible because it's in a tiny, tiny little bit of their visual field. So most of this isn't even visible to them, and it doesn't even look curved anyway between here and here. I mean, let's just look at how curved this looks between the observer and the horizon. That's how curved the Earth looks. And like I said, they don't even see most of it anyway because they're looking at it at such an angle that they can't see it. So I've demonstrated visually that there's no curvature to be seen. It's just too slight, even at this scale. Even a circle with a diameter of nearly 78 miles, the curvature's tiny, barely visible. And the curvature across their field of view wouldn't be visible. Now, just to finish, what I'll do is give you a sense of what the horizon looks like and how far it is below the horizontal. So again, remember what they're doing. They're taking a photograph of the horizon and they're using an angle of view from side to side of 90 degrees. So if we imagine what that photograph will look like, here's a comparison of the two. Right. So these two lines have got a length of 90 units, and I've placed them 0.56 units apart. So if the top line was, let's put it in the middle sort of roughly, yeah. So if that was eye level, exactly eye level, that's where the horizon would be. So that's eye level and that's the horizon. Sorry, that's eye level and that's the horizon. So I don't think that would be distinguishable to the naked eye, because you've got nothing in the distance to tell you exactly where eye level is or where the horizontal position would be in the distance. So it would look at eye level. Now also remember what I said. If, say, the top line was the actual horizon, then the person's looking at the Earth towards the horizon, and about 30 miles of what they can see will be between these two lines, and only about 10 miles up to this line. So they don't even see most of it, because they're looking at it at such a shallow angle. So for a person 1,000 feet above a sphere with a radius of 3,960 miles, the circle that they would see below them would look flat. They wouldn't see any curvature, and the horizon would look virtually at eye level, and without any extra indication of where eye level is, it wouldn't be noticeable that it was below eye level. So 1,000 feet covers most situations that people are going to find themselves in where they're close to the sea. Because remember, it's when you're at the sea that it's most obvious that the Earth is a sphere. And it's the part of the Earth that is most perfectly spherical is the sea. And so if you're anywhere near the sea, I don't think you're likely to be more than 1,000 feet. That's going to cover any hills or buildings, or even if you're in a ship or something like that. So the world will look flat to you because it's so big, even at this height.